Welcome everybody. Today we are going to talk about the module number 7, that is Sequential Logic Design, from the course of the Embedded System. The prerequisite for this module is a student must be familiar with the previous segment, that is a combinational logic design of this module. Once you are already familiar with the combinational logic design, the further knowledge about the sequential logic design will fully equip you to understand any embedded system functioning. So a sequential circuit, which is a digital circuit, gives output that are the function of the values of the current as well as the previous inputs. Elementary sequential circuit includes the flip-flops, which are commonly as D flip-flop, SR flip-flop, JK flip-flop. The other sequential circuit is registers and counters. The D flip-flop has two outputs, D and clock. When the clock is 1, that is high, the D value is stored in the flip-flop. The value then is seen at the output Q. When the clock is low, that is, it is going from high to low, the value of the D is not taken into account and the output Q retains its value. With this basic logic, the D flip-flop functions and can store the 1-bit input and has a memory of 1 bit. The SR flip-flop has 3 inputs, S, R and a clock. Consequently, the S stands for the set and R stands for the reset. When the clock is equal to 0, that is, the clock is low, the previously stored bit is preserved and shows at output Q. Whereas when the clock is equal to 1, that is high, the inputs S and R are examined. When the input S is 1, that is, it is set, a 1 is stored, and when R is 1, that is, it is in a reset condition, then 0 is stored. Whereas when both are 0, there is no change, and when both are 1, behavior remains unexplained for the SR flip-flop. The JK flip-flop is very similar to the SR, that is a set reset flip-flop, except that when both J and K are 1, the stored bit toggles from 1 to 0 or 0 to 1. The registers, it can store n bits from its n bit data input, and these stored bits emerge at the output. Normally, registers has at least 2 control inputs. These 2 control inputs are the clock and the load. In the rising edge triggered register, the input are only stored when the load is 1 and the clock is rising from 0 to 1. Few sequential components are shown in the figure, which has the n-bit register, the load clear, and the input is I and the output is Q. The output is equal to 0 if clear is equal to 1, I if load is equal to 1. Then there is the n-bit shift register, which shifts for the input bits. Here the triangle associated with a line at the input is the symbol for the clock. And there is a n-bit counter which count for number of ones which are appearing at input. So although a shift register stores n bits, they cannot be stored in parallel. Rather, they have to be shifted into the register serially, that is 1 bit per clock edge. A counter is a register which can be incremented, that is add binary 1 to its stored binary value, A counter has a very clear input in the basic form. This resets all the stored bits to 0. It also has a count of the input that supports incrementing on the clock edge. Hence, the counter can count the number of ones that are coming to the input. As discussed for the combinational logic design, the sequential logic design also has certain steps which are almost similar to the combinational logic design. The steps as seen in the figure are the problem description. So you want to construct a clock divider, show down your pre-existing clock so that your output is 1 for every 4 clock cycles. So here we want to design where the output is 1 for every 4 clock cycle, else the output is 0. In this case, instead of the truth table, we first go for the state diagram. The development for the state diagram and implementation for that state table will be discussed in upcoming modules. So, as for now, we just need to draw the state diagram, which is nothing but the portraying the connections between the input and the output according to the flip-flops or any sequential circuit which are to be implemented. Then the implementation and design. It includes two parts, that is a combinational logic, which is nothing but defining the output in terms of input, and the state registers, which will be making the combination logic sequential. Then write all this in terms of the state table. Again, once the state table is ready, we need to minimize the output equations which are obtained. The minimization can again, as similar to the combination logic design, can take place by the K-map. Hence, the final equations which is obtained after the minimization or not can be drawn as a combinational logic. In this way, the sequential logic design can happen. Thank you.